All right, part 2 of eigenvalues and eigenvectors. How do we find them? How do we find eigenvalues and eigenvectors? So let's do, for example, if x is an eigenvector of this matrix, 1, negative 2, 1, 0, 1, 4, 0, 0, 2, what does that mean? That means if I multiply x times this matrix, then I get lambda times x. Something we need to remember is that x is non-zero. Okay, if x is the zero, all zeros vector or all zeros matrix, then of course this is true. It will always be true no matter what. So we don't want that kind of solution. We want, if there's a non-zero one, an interesting one that will be true. So we want to actually figure out how we can figure out those x matrices. So what would that mean? Okay, it would mean that lambda x minus our matrix times x equals 0, equals a 0 matrix, has a non-trivial solution. Remember, the trivial solution is the all zeros matrix. We want to have a non-trivial solution. All right, so let's factor out an x. So lambda I minus our matrix times x equals 0 has a non-trivial solution. Now this should ring some bells. When do we have a matrix times x equal to 0 matrix have a non-trivial solution? When does that happen? It happens exactly when that matrix, this one, so it simplifies to this one, those two are equal. It happens exactly when that matrix is singular. Okay, that's the only time when we get a non-trivial solution there. Okay, so we want a lambda that makes that matrix singular. So how do we know if we have a singular matrix? It happens exactly when the determinant of the matrix is 0. Okay. We're trying to find eigenvalues now. We have an eigenvalue exactly when our lambda I minus our matrix is a singular matrix. And we're going to be able to figure this out when the determinant of that matrix equals 0. So in this case, we've got a triangular matrix, so we can multiply the diagonals, and that tells us that lambda minus 1 squared times lambda minus 2 equals 0. So this, solutions to this equation will give us our eigenvalues. Because this is such an important equation, we call this expression on the left, this is the characteristic polynomial. And we call the whole thing the characteristic equation. Okay, characteristic polynomial is just the expression on the left, the polynomial with the lambdas in it, and the characteristic equation is when we set it equal to 0. Okay, if we look at this characteristic polynomial, it's already factored for us and everything, so that tells us lambda equals 1 and lambda equals 2 are the eigenvalues. Okay, so now we have eigenvalues, and that's one step toward finding the eigenvalues and eigenvectors of our matrix. So let's at least find the eigenvectors associated with, say, lambda equals 1. Okay, so let's do that. Okay, actually, on second thought, I want to only look at eigenvectors associated to eigenvalues equal 2. We've already looked at a lot of cases where we have eigenvectors associated with eigenvalues of 1, and that's because we talked about those steady state vectors, and those are all eigenvectors with eigenvalues equal to 1. So let's try 2. So if we have an eigenvector with eigenvalue 2, that means that this matrix times x equals 2x. Or in other words, the all zeros matrix equals 2x minus 1, negative 2, 1, 0, 1, 4, 0, 0, 1 times x, which tells us that 0 equals 2i minus our matrix that big thing times x. So we get a matrix equation. Let's rewrite that a little bit to make it look nicer. Okay, if we rewrite that, I'm going to write the matrix on the left. We get 1s on our diagonal, 0s, and 2, negative 1, negative 4. That's 2i minus our matrix. X equals the all zeros matrix. And guess what? That's something that we know how to solve. Okay? Remember, this is just like taking our matrix, augmenting it with all zeros, and then row reducing. So, if we do that, we find that our matrix is, well, let's just write it out. We augment it with all zeros. This is row equivalent to. Oh wait, I see that I made a mistake, and hopefully you've already seen it too. And my mistake was right here. That was not a 1. That was actually a 0, because over here we had a 0 there. We had a 2. Sorry, this was a 2. And that was a 2. And that was a 2. And so then this becomes a 0. And so this becomes row equivalent to, let's see, 1, and then 0, and 7, 0, 0. Okay, so what does this tell us? It tells us that x1 plus 7x3 equals 0, and x2 minus 4x3 equals 0. So we could let x3 be our parameter t. I'm going to write this in vector form. Then x2 is 4t, and x1 is negative 7t, which tells us that all eigenvectors associated with eigenvalue 2 are some real number t times negative 7, 4, 1. And those would be our eigenvectors associated with eigenvalue 2. Okay, this process can be used in general to find all eigenvectors and eigenvalues. So you start with the characteristic equation, which we find by finding the determinant of lambda I minus our matrix and setting that equal to 0. That's our characteristic equation. This gives eigenvalues. Then we find eigenvectors for particular eigenvalues. By taking a particular eigenvalue and then solving lambda I minus a times x equals the 0 vector. So you're looking for all x that make this true. So we're looking for non-zero x from your choice of eigenvalues. From up here, solving that characteristic equation guarantees that there's some non-zero x that will make this true. Then that makes your eigenvectors. Okay, we'll do more of this in class. I hope this helped.